Okay, and welcome back to the Learning, Memory, and Development chapter, Chapter 9. Chapter 9 is the only chapter associated with this particular lecture, and it includes, of course, those three main categories, learning, memory, and development. That's the order that we're going to cover these three in, so let's get started on our topic of learning. Learning is defined as the process by which relatively permanent change in behavior occurs. And in fact, the term relatively permanent is really the key term in that definition because learning is all about change, not about stable functioning, but rather about your capacity to change your behavior. So as a result, what you see that's very indicative of a learning process is that you have the capacity to change, but not necessarily ever maintain one pattern of behavior over a lengthy period of time. In fact, if a pattern of behavior lasts over a lengthy period of time, that stability largely comes from an unchanging environment, or largely unchanging environment. But as it is, environments typically will change, and so your pattern of behavior will wind up changing. So the two things that always are focused on in the field of learning is acquisition and elimination. The acquisition of a new pattern of behavior and the elimination of an old pattern of behavior. And in fact, typically the elimination of an old pattern of behavior is usually met at the same time with the acquisition of a new pattern of behavior. Now, there are a variety of types of learning. Your text identifies non-associative, associative, and biological bases of learning as three general categories, and that's fine. You could argue the issue about non-associative learning. The reason there is a category of non-associative learning is because originally associative learning was developed. And associative learning requires two stimuli in the environment to be associated together in either space or time. And there's a couple variations here that you see, classical and operant conditioning, which we'll cover in more detail in the coming slides. But in general, you're probably typically familiar with it. Classical conditioning involves the work of Pavlov, who primarily started that area. And in terms of classical conditioning, you'll have something in the most common example, a bell ring and then food presentation for a dog. And as the bell rings and then the food is given to the dog associates the bell and the food together so that later on, whenever the bell sounds, it has essentially taken on some of the properties of the food itself. In operant conditioning, you have a scenario where an action is rewarded. So there's an association again, same type of association, but now between a response of the subject and some sort of consequential stimulus that occurs. So if a rat presses a bar and a food pellet comes out, the action of pressing the bar is associated with the presence of the food pellet. So what you're looking at in this case, in classical and operant conditioning, they're actually very similar to each other underneath. In fact, I could go on for hours about the theoretical similarities between the two, but we'll leave it at that for now. Now, this gets us back to the issue of non-associative learning that's on the top of the screen here. Non-associative learning was called non-associative because the human experimenters explicitly were not trying to associate two things together, like a bell and a food, or a response and a food pellet. Instead, in non-associative learning, the researchers back in the 1930s and 40s and 50s would just present a single stimulus to a subject and evaluate the effect of that stimulus on the subject. And that's why they called it non-associative, because they weren't explicitly associating it with anything else. The problem with that, theoretically, you should be aware of, although I guarantee questions like this are not going to show up on your MCAT. And it comes from the basics of learning, which is if you present a single stimulus, like a loud noise in a room with a experimental subject, that loud noise becomes associated with the room itself. And in fact, there's no way to not associate two cues together in any kind of scenario, because you're always presented with sensory information. And whenever a new form of sensation occurs, it's always associated with other things. That point was largely missed back in the 30s when this name non-associative developed. So there is essentially an associative process underlying it, but it has always been given the name non-associative, and people have just used that term ever since, despite the fact that technically it's incorrect. And then on the very bottom there, biological bases of learning, which is usually not so much of a topic any longer as time is changing. Back when that term, biological basis of learning, was developed, sometime around probably in the 40s or 50s, what you really saw was the inability to evaluate neurological function and how it relates to learning or memory. As a result, all of the research back in the 40s and the 50s was largely done based on overt patterns of behavior. Sound a bell, feed a dog, see if it salivates, and then work a system of knowledge based upon the environmental stimuli and the overt patterns of behavior of your subject. When people started to develop some of the technical skills, and this really is a issue of biology and the technological development more than anything else. As the technical skills developed to be able to address the underlying biological connections that were occurring, and the neuropharmacological ones and so forth, then a category of evaluation called biological bases of learning was developed. Because that type of scientific work is so common today that nobody even uses the term, because learning and all forms of psychology very clearly have underlying biological structures to it, and today you can actually evaluate them, even in the simplest case, by doing some sort of brain scan while somebody engages in an intellectual task. So effectively, all of psychology is turning toward a biological basis. The things that can be more easily grabbed up, like learning, memory, sensation, some perceptual aspects, those definitely are consistently being studied. And there's a variety of things that are just too far out there to really pick up on the underlying biological things, like a lot of the personality work, intelligence, and probably more than anything else, social psychology. Now, a lot of the non-associative work really gets started off in the 50s. There was work prior to that, as I mentioned earlier, going back at least to the 1930s. But in this case, the non-associative learning that your book focuses on largely has an underlying connection to biological research. And one of the individuals that did a lot of this work early on in the 50s was this fellow Eric Kandel, who won the Nobel Prize for his work after about nearly 50 years of research. In fact, I think his Nobel Prize was from the year 2000. But Kandel's story, just as a side, was a little bit amusing. Kandel, back in the 40s, was interested in why there was a rise in Nazism in Germany. And so he decided to get a degree in history from college. And while he was in his history degree, he kind of realized that history was not really explaining why people acted the way they did, so he should focus his attention on psychology. That way, if he understood psychology, he could blend it into history. So as he's studying psychology, he actually gets involved with some psychoanalysts. And, I've already gone through the whole story of psychoanalysis. You got to remember, it's the early 50s. They're still around for sure. But what the psychoanalysts tell Kandel is that if you really want to understand human psychology, you should become a psychoanalyst. And so he believes that, and he decides to become a psychoanalyst. But to become a psychoanalyst, you have to go to medical school, because Sigmund Freud was a medical doctor, and when he created the field of psychiatry, he said, well, you got to go to medical school like me, and then afterward do your residency in mental health issues. So Candel's on his way to become a psychoanalyst and talking about the Oedipal complex. And when he goes to medical school, he falls in love with biological research. And so he never carries on in his interest in terms of psychoanalysis as a way to understand human psychology, and psychology as a way to understand history, and history as a way to understand Nazism. Instead, he sticks with medical research, and that occurs in the mid-50s approximately, and he works on that area on some of the lowest level aspects of behavior, non-associative learning in a giant snail. And doing that work for 50 years kind of lays out some of the basic circuitry by which Pavlovian and operant conditioning function, at least as a general model for learning that can be applied to other creatures. And that's largely where his Nobel Prize comes from. He is kind of the leader in the field, the first person to kind of really set up that underlying integrated circuit that's in your brain that accounts for some of the lowest level psychological functioning, like habituation, you getting used to something and responding to it less and less over time, or dishabituation, while you're habituating and a loud stimulus occurs or something that's very strong, you wind up having a strong reaction to that cue again. Or sensitization, which is a very unlikely thing to occur typically. Sensitization is when a stimulus occurs over and over again and you actually heighten the degree of response to it. That's a very unlikely scenario. And then desensitization, which is a training process where you become sensitive to something, but then there's a separate component where you can eliminate the amount of responding to the cue. And that's essentially what's happening under these circumstances. Now, to build it up from non-associative learning, we'll go into the associative learning categories. The first being classical, the second being operant, where we'll actually spend more of our time. In terms of classical conditioning, it got started largely by Ivan Pavlov, and until recently, an unknown character showed up in the biography of Pavlov, and this is a fellow named Ivan Tolochinov. The two Ivans essentially worked together to do the first work on what we now call Pavlovian conditioning sometime between 1901 and 1902. Pavlov has always been largely credited for it, but what you really see is that Pavlov was doing much of the theoretical work as kind of the head of a laboratory, and Tolochinov was actually the hands-on person that conducted the first experiments themselves. So it was really the two Ivans working together. It's unlikely you'll hear about Tolochinov on your MCAT exam. In fact, in this case, you'll hear more about Pavlovian conditioning in general and less about any of the history that I'm feeding you on the side here. But the story of Pavlovian conditioning is fairly straightforward from a behavioral standpoint, which is, of course, the way in which it was originally developed. You take a hungry dog, the dog has to be hungry, and the dog will salivate to the presence of food. If you sound a tuning fork or a bell or some other thing, then that will not make the dog salivate, right? There's no reason why a dog would salivate to the sound of a tuning fork in and of itself if it's never been associated with anything. Then if you take the tuning fork and pair it with the food overall, what happens is the thing that makes the dog salivate, that is, the thing that is causing a response, always transfers its capacity over to the neutral cue, like the tuning fork, which does not make dogs salivate in and of itself. And so the tuning fork will start to take on the properties of the food itself. And so the tuning fork will be able to make the dog salivate. And it's a fairly straightforward thing. I think most people in society have a general idea of how this functions now, because it's so widely understood. What you're going to see in terms of this process is that transfer of control from the food over to the tuning fork essentially functions the same way as you charge a rechargeable battery. So if the tuning fork was analogous to a rechargeable battery, you could associate the tuning fork with the food, which is essentially charging it, and then you can use the tuning fork to make the dog salivate. And if you present that tuning fork to the dog over and over and over and over and over again, eventually the tuning fork, having never been associated with food again, will slowly lose its control, and then it'll just go back to being a tuning fork that doesn't make dogs salivate. You have to go back and reconnect or reassociate the tuning fork with the food again to charge it back up so that it can control behavior once more. As a result, you're always in this process of charging up the tuning fork and then using it and allowing it to discharge and then having to go back and recharge it again. That is, reassociate it so it gains its power back. It functions, analogously to a rechargeable battery, which of course you're very familiar with because we all have cell phones. So if you take a look at some of the most basic aspects of classical conditioning here, you'll see this figure which shows really two of the main things that you see in conditioning experiments. That is acquisition and extinction, because those are the principles by which behavior is changing. You don't see a portion of this figure where you have stable, consistent responding, because that usually gets associated with memory rather than learning. And we'll see memory soon enough in this particular chapter. Now, in terms of acquisition, what's happening is if, for example, we go back to that tuning fork, if a dog does not salivate to the sound of a tuning fork, you can make that happen by simply associating the sound of the tuning fork with the food over and over and over again. And as you'll see in this particular figure, what you'll wind up with is greater and greater salivation to the tuning fork itself over repeated pairings. Once the dog reaches some biological maximum to the amount that it salivates, because that's going to be largely your limit to tell that any learning has actually maxed itself out, that you're not going to get any more responding up beyond some point, you can then stop associating the tuning fork with the food and just use the tuning fork itself. What will happen initially is that you'll get a brief increase in responding, which is called an extinction burst. The reasons of why that happens is really not very important for our purposes here, and it's kind of a long-winded explanation, so I'm going to skip talking about that. But after that initial extinction burst, you're going to see a continual drop-off of the control that the tuning fork can manage with the animal. And again, if we go back to that rechargeable battery story, that's what you're actually seeing here. In acquisition, when you're pairing the tuning fork with the food, it's like you're charging up the rechargeable battery. When you start to use the battery by itself and you're not charging it anymore, it will simply discharge and it will lose its ability to do anything until it just goes completely dead. And that's a fairly straightforward story. Spontaneous recovery in the end, which also really kind of requires a long-winded explanation, which I'm just not going to go off on that side track to explain, because I guarantee you're not going to be asked for that much detail in the MCAT evaluation of this material. Spontaneous recovery is essentially this. When you pair the tuning fork with the food for the dog, there are other stimuli in the environment that are also associated with the food, like the presence of the room, or the presence of the experimenter, or the experimental chamber itself. There are other things that may not occur as frequently connected as tuning fork food, tuning fork food, tuning fork food, which is always a very clear association. But if you always do your work pairing the tuning fork and the food in a particular experimental environment, then that particular experimental environment is then associated with the food. So for the myriad types of slop, stimulus slop that occur for the subject that get dragged along in this entire process, many of them are going to control responding. So even though you may completely eliminate responding to the tuning fork itself, other stimuli in the environment will still manage some of the behavior, and that's why you see behavior come back after about 24 hours, because those other cues oftentimes are not extinguished at the same rate as the tuning fork. Each time you present the tuning fork, it loses some of its strength until it dies out completely. But if the experimental chamber where the subject is worked on is paired with food once a day, then to extinguish it, you're going to have to go through multiple days of pairing the experimental chamber with no food before that chamber completely loses its strength. And so that's why spontaneous recovery, as you see here, will maintain behavior over a lengthy period of time. Some of the other very basic aspects of classical conditioning, which is you're going to see in operant conditioning as well, are the principles of generalization and discrimination. Generalization and discrimination are two ends of the same continuum. So they are not separate processes. They are simply two ends of the same continuum. And there's going to be a little bit of a mix-up here in terms of the word discrimination. Generalization refers to a process by which you can't tell the difference between stimuli, and that's why the set of twins is on the screen. If you just met these girls and they were running around the room, you wouldn't remember who was Susie and who was Sally because they look so much alike, and you're not familiar with them, so you would be said to generalize between the two because you can't tell the two between them. If you were these girls' parents because you were there on the day they were born and you've literally seen them every day of their life up to the point now where they're 5 years old here, you would be able to easily tell the difference between them, and that would be discrimination, right? You could tell the difference between them, and that's called discrimination. The terms were originally in Russian because Pavlov had set up most of the initial vocabulary for classical conditioning, and then the Russian had to be translated into English. The original word that people used back in the early 20th century was differentiation, but for theoretical reasons I'm not going to go into, rather than saying differentiation, the word discrimination sounded like a better idea. Discrimination is when you can clearly distinguish between these girls. So maybe you are their parents and you've been around for their entire life. Now that they're 5 years old, you can tell the difference between them very easily because you have so much contact with them, and that's simply called discrimination, where you can tell the difference between one stimulus and another stimulus. So telling the difference between a red and a yellow light is discrimination. Telling the difference between Susie and Sally here on the screen is also discrimination. It simply refers in a technical sense to your ability to be controlled by the presence of two different stimuli that people might generally refer to as somewhat similar to each other, like a red and a dark red, for example. That would be in terms of light. Or if you're a musician, you can tell very easily the difference between a sharp and a flat, or a C and a D. And there's a lot of people that, of course, that are not trained musicians that can't make that difference, and so they would not be said to discriminate between those different chords or keys, but rather you would say they generalize between them. Now, in terms of operant conditioning, which is the second form of associative learning that is identified in your book, the work in operant conditioning largely gets started with a fellow named Edward Thorndike at about 1895. So notice that Thorndike started his work ballpark about 6 to 7 years before Pavlov did. Thorndike was an American who was largely working on his doctoral dissertation at Harvard University when he was interested in evaluating learning specifically. So from a historical standpoint, Pavlov, as you probably know the story, fell into the whole process of evaluating learning accidentally because his dogs were salivating and he didn't know why, and so he decided to study it. Thorndike, on the other hand, specifically wanted to evaluate learning because for the nearly 20 years that psychology had existed at that point, nobody was doing explicit studies on the underlying principles of learning. And so that's how he was making his dissertation. And so he was evaluating a lot of different animals and different scenarios. And in fact, to a great degree, had kind of a background interest in evolution and how that would influence processes of learning. Most of that work doesn't actually get highlighted in his historical description. Typically, Thorndike is just identified as the person that discovered operant conditioning. Now, Thorndike's work, called operant conditioning or instrumental learning, those are simply two terms that mean the exact same thing. And that's very important that you're aware of that, because typically books do not distinguish very well between the two, and you may be led to believe that operant conditioning and instrumental learning are different things. It simply is a theoretical difference that led to the rise of the term operant conditioning being used today, in arguing that actually took place back in the late 1930s with B.F. Skinner. But in this case, where Thorndike came up with the term instrumental learning was the idea that in an abstracted sense, your capacity to learn was a tool, and that tool was applied to the environment so that you could adapt to environmental conditions. So you're using your learning capacity as an instrument on the environment, and that's where instrumental learning comes from. That, for, again, theoretical reasons, was argued up until around the 1930s, when largely most people sided with a new term, which was operant conditioning, that came from the idea that behavior operates on the environment. The reason why operant conditioning won out is because it's a cleaner scientific description. It doesn't engage any sense of what might be going on in the brain. So to eliminate any kind of mentalistic concept from psychology back in the late 30s, which was really kind of a big deal, because you have to remember one of the most popular people in psychology in the late 30s was Sigmund Freud. And nothing that Freud suggested really involved much in the way of overt behavior. It was all about mental activity. And can you see a person's thoughts? No, you can't. And that keeps mental activity out of the realm of direct scientific reasoning. So the big deal in this case was to re-describe what Thorndike did and call it operant conditioning, because the behavior operates on the environment, rather than making an assumption that learning is an instrument that can be applied in an abstract sense, because that implies thinking. And since you can't see the thinking, you simply can't talk about it if you want to be a good scientist. You just have to recognize that sometime in the future, maybe somebody will find a way to think about thinking, or to actually measure thinking directly. And by the way, if you're wondering about that, the answer is that still has not happened. There's not a single brain scan that truly indicates thinking. You can simply only find areas of the brain that become active during certain types of thinking, but what you're really looking for to try to measure thinking directly is to be able to read some kind of information off a person's brain and say, oh, they were reciting the Pledge of Allegiance in their head even though their lips weren't moving. Right? That's ultimately what you're trying to shoot for, and that kind of technology simply doesn't even exist now. So we're certainly 90 years into that argument and still don't have the technology to be able to identify an internal thought properly in a scientific fashion. Now, in the work that Thorndike did, he worked with cats and made himself what he called a puzzle box. The puzzle box, very simply, is a wooden cage, nothing more than like a habit trail is for a hamster. It's not a harmful device. He just basically made a wooden cage, put a cat in it, and locked him in. And the cat was able to figure out how to get out by stepping on a little pedal and flipping a latch on the door, and then the door would open up. So it was designed as a way to give the cat an opportunity to express its capacity to learn. That was why it was called a puzzle box. The cat had to figure out the puzzle of getting out. And the way that Thorndike measured learning was simply to measure the amount of time that it took for the cat to get out. So the cat is placed in the box, he's locked in, and then Thorndike simply steps back, starts a stopwatch, and waits for the cat to figure out its way to get out. Now, why does the cat want to get out of the box? Well, because Thorndike didn't feed it. And right outside the cage, a plate of raw fish was placed. And, of course, back then, there's no fancy feast or Alpo for Kitty. So the cat wants to eat the raw fish, and it starts moving around and investigating the box. Now, you don't know what the cat might be thinking or experiencing, but what you do see for sure is that you will increase the amount of activity of the animal under a case like this when you haven't fed it for, let's say, 12 hours, and then you put food just outside of its reach. Eventually, the cat will go through a whole series of what are generally referred to as trial and error responses, and eventually it's going to produce a sequence of behavior that will wind up opening the door. The cat will get out, eat the fish, and then Thorndike will come along, throw the cat back in the box, lock him in again, start the stopwatch over, and then wait for the second trial to be done when the cat gets out and gets to eat the fish again. So you do this over multiple times a day over the course of many days, and what you wind up seeing is the very first learning curve, which is the cat takes a long time to get out of the box initially, and generally over time it learns to be able to do so faster and faster until you reach a point at which the hungry cat is shoved in the box, it's locked in, and it just turns around, opens the door immediately, and comes right back out. So that's the way that learning was originally developed in these operating conditioning paradigms. Now, because Thorndike is working with the need for the subject to exhibit a pattern of behavior that leads to a consequence, Thorndike's focused on some type of general association that occurs between a response and a stimulus. So if you look here on the bottom of the slide, what you wind up seeing is that there are three general things Thorndike focuses on primarily. One, the presence of the box itself, which is called an antecedent stimulus because it always precedes the response in question. Then escaping is the response. Response is kind of the center of this three-term contingency. And then the consequential stimulus, in this case, is going to be food. Now, the consequential stimulus is always called consequential because it's the response. It is the stimulus that occurs immediately after the response in question occurs. So there's an initial stimulus that's before a response, the response itself, and then a new stimulus event that occurs after the response. So everything in terms of antecedent or consequence is determined based upon its time relation with respect to the response that's necessary in the experiment. In this case, escaping was considered the response. So much of operant conditioning has, over the decades, been focused on the association between a response and the consequential stimuli. There has been other types of work between the antecedent stimulus and the response, and the antecedent stimulus and the consequence as well. And in fact, just out of curiosity, just to throw this out there because you might be interested, if you had taken the Pavlovian evaluation of associations itself and applied it to the three possible stimuli in the operant conditioning scenario, you then have what's referred to as a Pavlovian description of operant conditioning. That you would have an association between antecedent response and an association between response and a consequence, and an association between the antecedent stimulus and the consequential stimulus. And that would kind of give you a different theoretical view of operant conditioning. That kind of work is not going to be on the MCAT, but you may be noticing that that's a possibility in a scenario. And it is something that a number of people have actually worked on over the years. Now, one of the things that really comes out of the whole story of operant conditioning is the issue of schedules of reinforcement. Initially, in Pavlov's work, you typically see some cue, like the tuning fork, and the food being associated in a one-to-one correspondence. That is, every time the tuning fork occurs, the dog is going to be fed. And during an acquisition process, obviously, not during extinction. Now, in the operant conditioning process, one of the questions was whether or not the rate at which the consequential stimulus occurs after responses is going to be a determining factor in how quickly the subject learns or even how quickly it extinguishes its behavior, largely came into being sometime during the 1930s. And as a result, you saw the growth of this subfield of conditioning called schedules of reinforcement, because schedules of reinforcement are all about the relationship between responses and consequences and the probability between them. So you make a response, what's the probability that a consequence will occur? If it's a 10% chance, then you're going to have to produce, on average, about 10 responses to get one consequence. How does that affect the development of learning? How does that affect the development of extinction or generalization or discrimination? And in fact, these schedules of reinforcement affect everything. Turns out that they have a very broad influence across the board, and as a result are really a primary aspect of study even today. Now, your text covers 4 of the most basic types of schedules of reinforcement that you see in operant conditioning work. There are actually many, many more. And in fact, you are largely limited to your imagination as to what type of schedule of reinforcement you can actually create. Largely because when you evaluate schedules of reinforcement for real people in the real world, you actually see a wide array of events that occur for an individual based on their behavior. And so analogs to these real scenarios actually get conducted in the laboratory with rats or pigeon subjects to evaluate how these different systems operate. Now, the 4 most basic schedules of reinforcement that we look at are the fixed ratio, fixed interval, variable ratio, and variable interval schedules. So they're always fixed or variable, and that's always the adjective in this description, and that's always ratio or interval. As we'll see, fixed and variable mean largely just what you might think. Fixed means it's always the same. Variable means it's always changing. Ratio implies that there's a set number of responses that must occur before the consequence can occur. In interval schedules, there's a period of time that must go by. So what you're really looking at between, let's say, a fixed ratio and a fixed interval schedule is that it's fixed, so it's always the same, but in terms of ratio, there's, let's say, 5 responses you have to do. And if it's an interval schedule, then it might be a 15-second wait that you have to get through. And that largely kind of sets up your understanding of how these 4 schedules operate. In terms of the fixed ratio schedule, you see them abbreviated typically this way, like FR7, FR25, indicating it's a fixed ratio schedule in which 7 responses must occur or 25 responses must occur before a consequence can occur. A nice example of a fixed ratio schedule for using a telephone back in the 1970s, for example, required you to dial 7 numbers on a rotary phone before your phone call could go through. So there was no way about that. If you dialed 6 numbers, no call went through. And if you dialed 8 numbers, call might go through, but the 8th one might actually throw it off depending on when you started to dial it. So there was 7 numbers that had to be dialed, and then only would you actually make a proper phone call. And that's a fixed ratio 7 schedule. If you think about your keyboard, when you type, it functions on a fixed ratio 1 schedule. Each time you press the letter M or K or Q or the number 5, you expect that symbol to appear on the screen. It's a fixed ratio 1 schedule. Each response produces a consequence of that symbol up on the screen immediately. If you had a keyboard in which you had to hit every key 3 times before the symbol would show up on the screen, you would get it repaired or throw it away because that's a garbage keyboard, right? Nobody would actually tolerate that. You want to be able to press the key once and then get the symbol you need. So that's a fixed ratio 1 schedule. And typically, if you are in control of the consequences you obtain, then that will generally produce a high rate of responding. So if I told you that for every time you press a button, I'm going to give you $5, you could be darn sure that you're going to press that button as quickly as possible to earn as much money per unit time as you possibly can. And so typically in scenarios where you have some consequence the subject wants, you do get high rates of responding with fixed ratio schedules. In a fixed interval schedule, you're just moved to a fixed period of time. Interval simply means time. So some length of time must pass in which you can't speed it up or slow it down. You have to let the entire time period pass, and then a single response will generate the consequence that you're trying to get in this case. So you oftentimes see this abbreviated like FI 10 seconds or FI 15 minutes, indicating the time length that has to occur before the consequence will occur. Here are some examples. If you're a rule follower and you go to 7-Eleven and it tells you, if you take one of the burritos, you have to microwave it for 90 seconds. You can't speed up or slow down 90 seconds. It doesn't matter how hungry you are. You've got to wait the whole 90 seconds before the burrito is sufficiently hot, and you can eliminate all the salmonella and all the other diseases that are inside that 7-Eleven burrito. If you stop at a red light, you can't speed up the rate at which the traffic signals change. In fact, you'll probably have to wait about 2 minutes before they run through their entire cycle and you get a green light. If you go into a class that's 50 minutes long, and generally your instructor takes 50 minutes to cover the entire class, you can't speed up the time or slow it down. You must wait the 50 minutes before you can stand up and walk out to go get your lunch or do something else. There's nothing you can do about that time sequence. You simply have to let it go. So what you oftentimes see is that when it's clear that you're in the schedule itself, especially at the very beginning of the time period, you'll get very little responding out of the subject because no response that occurs at that point will meet a consequence you're trying to get. But as you get toward the point at which a consequence can occur, then you're more likely to see more and more responding over time. In fact, it is schedules like this that have proven beyond a shadow of a doubt that basically anything with a nervous system, even if it doesn't have a brain, can still measure time to some degree. Because you could put a jellyfish on a fixed interval 15-second schedule and train it to be able to obtain food on that period, and it will measure its behavior in a proper way to acquire responses in that schedule. And you know that it measures the time because it'll do very little at the very beginning of the 15-second period, and its rate of behavior will increase as the time toward reward occurs. And that's certainly true with anything that has a brain as well. So if anybody ever asks you, do you think elephants can tell time? They absolutely can. In fact, it's just a common property of a nervous system to be able to measure time. And so anything with a nervous system can definitely tell time. Now, a variable ratio schedule. With variable ratio schedule, it works just like the ratio schedule we already talked about. You know, a fixed ratio 5 just means it's always 5 responses before you get your consequence. In this case, with a variable ratio, there's going to be some variability around the mean number that you're actually working with. So, for example, in a variable ratio 27 schedule, that simply means that there's going to be other numbers that will average together to 27 that you're going to be exposed to that will ultimately be part of your experience in the schedule. So if you had a run through a schedule of either 26, 27, or 28 responses and had those three and always reused them equally, it would always average out to the number 27. And so it would be a variable ratio 27 schedule because 27 would be the average of the numbers 26, 27, and 28. But literally, sometimes you would actually get a consequence after 26 responses or 28 responses or even 27 responses. So in most cases, the variability around the mean is actually very important and has a great deal to do with how much behavior you can get out of the subject. But none of that's actually discussed in your book here. I think that's just a level of detail MCAT's not worried about. But just know with a variable ratio schedule, there's some number of runs through a system that are going to be below or above the average number. And that's all that really matters. For the most part, that will actually slow down the amount of responding you see with the subject simply because, you know, if you had 10 responses to get $1, then you know exactly what you have to do to be able to get the consequence. But if there's a wide range of consequences across the board, it tends to slow a person down. So let's say if I had two individuals, one who had to respond on a bar, press a bar 100 times to get $1, and another person who was on, and that's a fixed ratio 100, and compared that with a variable ratio 100, where you could get $1 after one response or two responses or three responses, so on, all the way up to 200 responses, right? Which if you took all the numbers from 1 up to 200, average them together, it would give you a variable ratio 100. For the person on the variable ratio schedule, sometimes they have to respond 175 times, 200 times, 160 times, and that will tend to cause the person to slow down overall. So the person on the fixed ratio schedule will respond at a higher rate than the person on the variable ratio schedule, even though the averages are exactly the same. Where you see these things play themselves out, these are actually very common in typical human behavior. You see them in slot machines. In fact, slot machines play this way. They are originally mechanically driven, now completely based off of computer programming to pay out at a certain rate. And that rate is determined by some range of numbers that's pulled out of a list in the computer system that will average out to something. And that's the way the slot machine operates. So, if somebody thinks that they can yank on the arm on a slot machine and to make it pay out, that's superstitious behavior. The slot machine pays out when it's designed to pay out and doesn't pay out at other times. If you were looking for meeting dateable people in a nightclub, it essentially operates the same way. You go to the nightclub and you're thinking, all right, I'm going to go home with a boyfriend or a girlfriend. I'm going to start trying to meet people and get phone numbers. This is basically, it's a variable ratio schedule. You go up to somebody, you start talking to them, you try to get a phone number, you either fail or you get one, and then you move on to the next person probably and start the whole sequence over again. All right, and even if you're not doing it the same night, you're going to have a sense of how easy it is for you specifically based on what you look like and your age and how good your rap is when you're at the club to be able to get somebody's phone number or to, get a date. And as a result, all those variables put together, which are even some things you're not even going to be aware of that may function in a non-conscious fashion, are going to influence whether or not you actually get the consequence you're looking for, which is the phone number. Same sort of thing happens when you ask your parents or your friends to borrow things. If you're always bothering your parents for $20, they may occasionally give in, and then they'll call you annoying. But the reason you ask for $20 all the time is because they give in. Maybe at a slow, steady rate, but they still reward you. And by giving you the $20, they actually are maintaining your pattern of annoying asking behavior. So not only can you get the $20 out of your parents, you can then blame them for you being annoying. Tell them I said that. Okay, so as you might imagine, this is going to produce a fairly slow and steady rate of responding over time. And the last schedule, the variable interval schedule, is one in which you now have a variable rate. So there's going to be some range around an average, but it's going to be time tables that you're going to be getting through. So a variable interval 10-second schedule, to give you again a simple story, could involve runs through the system of 9 seconds, 10 seconds, and 11 seconds. And honestly, that's not a realistic example from an experiment, but that just gives you the basic math to understand it. If you add up 9, 10, and 11, it'll average out to 10. So if you use each one of those three numbers exhaustively and then restart them, your average will always be 10, but it'll be a variable interval schedule because you have runs of 9, 10, or 11. Realistically, if you were doing a variable interval 10-second schedule, chances are you're going to have numbers from about 1 up to 19 or 20, whatever averages out to 10, and you'll wind up with that type of schedule designed into a computer program that's operating the equipment. You do see things like this in your real life, like when you wait for a mechanic to fix your car, right? No mechanic who, even being honest, says it's going to take about an hour to do the work on your car, honestly believes that means exactly 60 minutes. And in fact, if you're told that your car's going to be ready in an hour, you probably know realistically it could take 2.5 hours. If you go to Tire Kingdom to get one tire, you could be there for 3.5 hours. simply because there's other people in front of you. You know, it would take nothing for the people at Tire Kingdom to swap out a tire. But of course, you know, respectfully, you have to take people as they come in. And so it may take half your day just to get a new tire. So the length of time is never going to be set. It's always going to vary. It's always going to be variable, even if it's the same thing, like an oil change at Jiffy Lube, which is never going to take 15 minutes, and it's never going to take an exact amount of time that the mechanic tells you it's going to take, because there's all sorts of different things that have nothing to do with your car affecting whether or not your car comes out, like how much work another car in front of yours is going to take, whether or not somebody comes into work late, whether or not they're going to sell services to somebody else and to keep the car in the lineup for a long period of time, whether or not somebody uses the restroom is going to slow down when your car comes out of the shop. So there's lots of variables in a realistic sense that wind up affecting these things, and they all influence you. Waiting for customers to arrive at your register, you know, you probably, very similar to myself as an undergraduate, you know, I worked at a Wawa, and you know, a long, boring day is one where nobody comes in and buys anything because you just stand there stupid, you know, wrapped up in your own thoughts. It's better that people come to your register on a fairly regular basis, keeping you busy, and time seems to go faster that way. Even waiting for your phone to ring, or if you wanted to think about how often do you get a text on your phone? Well, the texts come to you largely outside of anything that you can do. You have a bunch of friends, and some of them may contact you during the course of the day. If you were to record when texts occur on your phone as a stream over the course of the day, you could simply measure the length of time in between each individual text, add them up, divide by the number of texts you have, and you would know what the average rate of time between texts occurs. And that's essentially the variable interval schedule that you're operating on. If you get a lot of texts, you probably are nervous about getting texts while you're driving. You're always looking at your phone. If you misplace your phone, you become anxious very quickly because there's always conversations that are going on that you may get cut out of if you don't quickly answer a text. But if you don't have very many people texting you, then you probably become much less anxious about misplacing your phone, right? You misplaced it in your house, not like you left it at McDonald's or something and somebody maybe steals it, but it's in your house, no big deal, right? Nothing is coming. You're not expecting anything important. It's no big deal. Your phone is probably in the bedroom or in the kitchen table, and it doesn't matter that you don't know where it is right now. Now, one of the last things that you see about operant conditioning that does have a very significant issue to it are those consequences themselves. Consequences so far have just been described basically as food items that you pick up along the way while you're responding. But you don't always have food as a consequence. And in fact, as you might imagine, electric shocks are common consequences in psychological research, at least in the early 20th century. It's actually much more difficult to do research where you electrocute your subjects anymore, and damn near impossible to do it if they're undergraduates any longer. Not since around the 1970s have you really been able to electrocute undergraduates, which I think is a real shame because they scream so nice. Anyway, if you take a look at consequences here, you probably remember this exact same slide from a discussion of consequences in a previous lecture, and this is exactly what you were looking at in the past. There are two primary factors to concern yourself with. The effect of the consequence on the future probability of the behavior, which is either to increase it or decrease it. And if it increases it, it's always called a reinforcer. And if it makes it less likely to occur or decreases its chance, then it's always called a punisher, which is simply a technical term meaning that it will eliminate the behavior. And the response that you exhibit either gains you access to or removes access from something. If you gain access to something, it's called positive because it's added to your environment. And if you lose access to something, then it's called negative because you lose access to it, so it's removed from your environment. And that gives you 4 possible consequences: positive reinforcer, positive punisher, negative reinforcer, and negative punisher. And something like a negative punisher certainly sounds like it's doubly bad because it's both negative and a punisher. But you have to be smarter than that and recognize that this is just a technical term that refers to a scenario in which a person's behavior has caused a loss of access to something which would make it less likely for them to do that in the future. And so, a simple example would be when you offend somebody, right? So your boyfriend or girlfriend, you say the wrong thing to them, like, gee, your makeup looks horrible today, or, God damn, are you getting fat? And then that person withdraws attention from you. That withdrawal of attention, if it actually has its desired effect on you, is going to get you to stop saying offensive things to your partner because they are withdrawing attention. That's the negative aspect. And the punisher is its effect on you, which makes it less likely that you make these offensive statements. Now, in terms of conditioning, there's kind of a final statement here about that wraps things up. These are mostly just terminology used over time. And as I've mentioned, even this term like biological basis of learning is a general term used today. It's not quite a distinct term any longer, largely because the expectation that research is being done on the underlying circuitry of learning and memory is just a given today, and everybody knows that eventually your understanding of learning and memory will probably fall on a basic integrated diagram of circuits that exist in your brain. Nobody generally goes around talking about biological bases of learning much any longer. But there are some old terms that kind of are still retained in the area, like biological constraints that are based on biological bases of learning. Like things like some creatures cannot do certain things because they literally don't have the sense receptors or even the circuits in their brain to be able to do them. One, for example, is you as a human being do not have sense receptors for magnetism. And so you could not determine from the Earth's magnetic field which direction was north. But many migratory birds can do that. And so that would be a biological constraint on your behavior. A nice one, of course, is missing brain circuits for language that largely don't occur in any creature other than human beings. So we have a language center. It's integrated in a certain way which is distinct from all other creatures on the planet. And that gives us the capacity for language, and it also, the missing circuitry also eliminates the opportunity for language to occur in any other creature. So of course you going to medical school probably have the plan now, hey, maybe I can get some gene studies going here and make dogs that talk. And have at it. They may not speak English like we do, but they will certainly be able to communicate in a language basis if that circuitry actually existed there. There'd be no reason to think that you could not give language to non-humans. But whether or not a dog is going to be able to make the exact same sounds we need for English or Spanish or French or any other human language is slightly different, but who cares, right? You give them the language center, they'll come up with different sounds, and then you'll be able to talk to your house pet. Oddly enough, not a story you hear much about in science fiction stories, but absolutely no reason why that should never actually happen sometime in the future. Food aversions. There are a wide range of foods that most creatures will actually eat, but there are things that there are much more preferred, and in fact, food aversions occur largely as a result of some basic stimulus properties like rotten meat or really feces and urine generally are avoided by most creatures, and certainly by human beings as potential food items. Part of the story of food aversions in terms of conditioned taste aversions that you'll see in the chapter function exactly the same way as basic classical conditioning. So when you read the section on conditioned taste aversions, don't be confused that it functions in some way unique in and of itself. It doesn't. Conditioned taste aversions operate on exactly the same rules of Pavlovian conditioning, except instead of operating on the order of seconds, where most classical conditioning actually operates, food or conditioned taste aversions, I should say, actually function up to a 24-hour time scale. But it does function by the exact same rules of Pavlovian conditioning. And so it's just an easy extension for you to understand Pavlovian conditioning. Know that most of that work takes place in the order of seconds. And then if you take one particular scenario where there is a taste and a gastrointestinal influence, so like feeling sick, tastes and sickness can be connected together in Pavlovian conditioning over a 24-hour period. But everything about conditioned taste aversions follows the same story as basic Pavlovian conditioning. And then mirror neurons and vicarious emotions. Those are aspects that really largely start showing up in the 1990s when mirror neurons were actually first identified. Clearly, from a behavioral standpoint, an individual, as well as many animals, can actually witness another creature do something and then copy it. And that's just called observational learning. Simple. Nobody really makes a big deal out of that. But how that actually occurred has always kind of been open to debate. In the 90s, a specific circuit of neurons that largely exist in your temporal lobe were discovered that are always activated anytime you watch somebody else do something and then learn how to copy it. Even in a mirror scenario where the person does it facing you, you can copy that person's behavior and rotate it 180 degrees so that your behavior matches that other individual perfectly. And that comes through the use of mirror neurons. And if you damage the mirror neurons in the temporal lobe, then a person loses the capacity to do observational learning. That seems to have some influence on emotional responding as well. It's a little bit more of an open question regarding the specific circuitry regarding emotions, but what is true from a behavioral basis is this. If you see someone sad, there's a good chance that you'll start to feel sad. And if you see somebody happy and laughing, there's a good chance that you'll actually start to feel happy and start laughing yourself. So seeing somebody else's emotions causes you to duplicate the same types of emotions yourself. That's normal patterns of behavior. Now, whether or not there's kind of an emotion type mirror neuron, or if it's the mirror neurons themselves that actually help this occur, is still kind of open for debate. But the basics of the behavioral process is clearly there. It's just not clear what some of the underlying biological principles are. And one of the last things about learning as well, whenever you hear about learning, if you're in a biological psychology textbook, you will always hear about long-term potentiation. And long-term potentiation simply refers to the additional increase in activity of a cell as a result of associations occurring. So if you pair a tuning fork with a food for a dog and find in the brain where some of these associations are actually taking place, the place where the tuning fork and the food kind of meet up in the circuitry becomes an area of cells that will generate more activity whenever tuning forks or foods occur. As a result, the increased activity in those particular synaptic areas is called long-term potentiation, because you have a longer period of increased activity at those specific junctions. That in general gets lumped in with the general term plasticity or neuroplasticity, which refers to your brain's ability to rewire itself as part of the underlying circuitry that gives you adaptive behaviors to meet the demands of the environment. So plasticity, neuroplasticity is the broader story. Long-term potentiation is kind of a specific type of neuroplasticity, or it's kind of a part of a subtype of overall plasticity that occurs. And that largely ends the section on learning before we move on to the memory section. And so I'll stop here and we'll pick up again in the memory section.